So I did all the unit conversions for you because I don't feel like that's something we should be worried about too much. Key thing to notice is that when we were at rest at the beginning, we were 14.5 pounds, therefore 64.5 newtons. In the middle, we went back to that. And actually at the very end, we went back to that too. So we started with this as what the scale was reading. It dropped, went back to what it usually would be, and then increased as we were stopping. So in order to understand this, I'm going to draw the two force arrows that were in the picture I had before. I'm not going to bother to draw the scale in the books anymore because what we really care about is the forces. A picture like this where you just draw the forces is sometimes called a free body diagram. So at the beginning, we're back where we were before. We had a normal force, and we had the force of gravity. And they're balanced because that elevator was standing still, nothing was going on, and since the books weren't moving, there must have been no unbalanced pull up or down. So we translate that into an equation, something we can solve with, by just writing Newton's second law. We just basically write sigma F is ma. This case, it's actually pretty simple. We got to pick a direction. I typically like to call up positive. We'll call down negative. And that means that we replace sigma F with Fn. Notice it's plus because it's up, minus Fg. And all that equals ma. But what's A? Nothing's accelerating. Nothing has any change in its motion at all. A is 0. So we're left with Fn minus Fg is 0. And not surprisingly, Fn equals Fg. So that's kind of interesting. What we intuitively thought, that the upward and downward pulls must be identical, actually ended up being what happened. What about these periods? Well, what was going on there? In those periods, we actually had the elevator accelerate. So let's start with this one. We know the force of gravity has the same size because the books didn't lose any mass. The Earth didn't pull on them less. So what must have dropped? Just that normal force. So this kind of looks like a tug of war that the top force is losing. And it's got to be, because we were not in motion. We were objects at rest. We wanted to stay at rest. And all of a sudden, we accelerated downwards. That means gravity must have won. It's not that gravity got bigger, it's that the normal force got smaller. The whole floor fell out from under us. So we'll have to add in a little downward acceleration. So what's our sum of force equation look like there? Still sigma F equals ma. This part's the same too. It's still an upward normal force minus downward gravity. But now A is not 0. In fact, we expect A to be some sort of negative number since it's pointing down. Let's find out what it is. So the normal force apparently was 57.82 newtons. What was gravity? Well, let's just use what the scale said when the scale was working normally. Minus 64.5 newtons. And all of that equals ma. So 57.82 minus 64.5, that's minus 6.68 newtons, and that equals ma. Since I got the mass as 6.59, that means now I can solve for what the acceleration was. So all we got to do is divide both sides by 6.59. And we end up with minus 1.01 meters per second squared equals acceleration. So it looks pretty complicated, and it's always fun to leave these things up on a board for when somebody walks in. They're like, whoa, you did something really amazing. But I just want you to kind of focus on the process by which we did this. I drew the picture. I asked myself which force must be winning. Well, the downward force. So that made me know that the normal force would be less. From my picture, I replaced sigma F with a list of forces. Upwards got positive, downwards got negative. I just plugged in the values I knew, and I solved for the only thing I didn't. So I actually know that the elevator has an acceleration downwards of a little more than 1 meter per second squared. Now what's going on here in the middle? This is mostly a lecture about Newton's second law, sigma F equals ma, but that's a little bit of Newton's first law. You were an object at rest. To start moving, what do you have to do? Accelerate. But now you're an object in motion. You don't have to keep accelerating. In fact, if you did, you would probably be going dangerously fast and would splat into the bottom of the school. So instead, once you become an object in motion because of this short period of acceleration, then there's no acceleration at all. The elevator starts moving at a constant speed. And in that case, with zero acceleration, we're right back to what we were before. Equal upward and downward forces. It's a little bit strange. Sometimes people think you need a force in order to be moving. And our experience shows that because in real life we've got to deal with things like friction. If you push a box, it doesn't just keep going forever. But that is what the laws of physics say it should do if there was no force of friction. So you were at rest, you had balanced forces. To move at constant speed, you also have balanced forces. In fact, for the time the elevator is moving at constant speed, I think you could see on the scale, there was no difference in the reading. We couldn't even tell that we were moving. It's only during the acceleration period that we feel weird or that we get funny results on a scale like that. So I'm going to cut away. I'm going to solve what the acceleration was during the stopping period, and I'll discuss that in just a bit. And then we'll summarize. All right, so I did my last calculation. Now we must have a larger upward force. The upward force must be winning the tug of war. And the reason for that is we were going downward. So if you wanted to stop us, you had to push us back. And back is upwards. So larger upward force, same size gravity as I had in all those cases. So plugged in the number for Fn, plugged in the usual weight for Fg, and plugged in the mass, and I got an acceleration upwards of 1.69 meters per second squared. So the bottom line behind all of this is it looks complicated, but it's a process. Sigma F equals ma becomes your list of forces. And the point of that is that all the forces there together are what cause the acceleration. So this is the way of taking them all into account. Picture sigma F equals ma, list your forces. You'll always have enough equations to solve. And once you've got this written out, as scary as this looks, it goes back to really being an Algebra 1 type problem. We're going to practice this a lot. There'll be a lot of examples for you to do. And if you get comfortable with this, It's really going to have you set up well for problem solving for the whole rest of the year.